Hello, students. In this video, we will cover learning objectives 3 and 4 from Module 2 and look at how do the parts of your brain function. So we're going to begin with the spinal cord. And as it says here, spinal cord is the gateway for information between the brain and the body. It's a thick bundle of nerves that conveys signals, from the brain to the body and from the body to the brain. It's kind of like I always. I'll just give you how I think of it. I think of it as like a really fast elevator shaft. I mean, the you need to send signals quickly to reach your legs or your arms or any other parts of your body that you want to move, and you need to get signals back from those parts to know, whether you've just stepped on something hot or sharp or and so speed is really important, and the spinal cord allows for quick messages to go up and down between your body and your brain. The nerves that carry information from the body up to the brain are called sensory nerves. Sensory nerves. The nerves that carry information from the brain to the rest of the body are called motor nerves. So we have sensory nerves that go to the brain and motor nerves that come from the brain. Also, your spinal cord contains what's called interneurons, interneurons, interneurons. These neurons allow for reflexes to happen, where you can, make a sudden move based on stimuli, even though your brain hasn't received the message yet. For instance, they sometimes test it, your reflex. If you're in a doctor's office, they might do one of those knee tap tests where all of a sudden your leg kind of kicks out. Well, you didn't decide to kick your leg out. It happened from your spinal cord. The message from the doctor tapping on your knee in the right spot, it went up to your spinal cord, and then the spinal cord sent a signal right back down for you to move your leg. The reason we have interneurons is mainly for protection. I guess is there are they tend to come into play in dangerous situations. Like, let's say you were to put your hand on a stove, on a burner, let's say. You want to move that hand as quickly away as possible. If you wait for the signal to travel up to your brain, and then your brain would have to register, oh, my hand's really hot, and then you would send a signal back down to move your arm. Well, that would just take a little bit longer than the path to the spinal cord. So what happens is that if you were to put your hand on something hot, the message travels to your spinal cord, and then there's a interneuron that sends a signal back down to jerk your hand away. Same thing with your feet. These are the main purposes of the interneurons are really for your limbs. You step on something sharp or something hot, the interneuron is going to cause you to quickly lift your foot up before the message even reaches your brain. So you would actually begin moving your hand or your foot away from something hot or sharp before it's even registered in your brain. Before you even feel it, you would start the movement of jerking it away. So it's a protection device, in a sense. And and so we have certain reflexes that help protect us from more serious injury when time is really important. Okay, those are interneurons within the spinal cord. Okay, let's move on to the hindbrain. We're going to talk briefly about the hindbrain, and then the midbrain, and then the forebrain. Okay? So there are three sections of the brain that we will talk about in the so the hindbrain, you can see in the picture here, it's really low down. It's the first thing you get to as you travel up the yellow colored spinal cord here. You reach the hindbrain, and it's located below the midbrain, which we'll look at next. And the hindbrain is the most primitive part of the brain. And what I mean by that is that through evolution, our brains have gotten bigger, you know, during the whole time that man has existed. And our brains have expanded outwards. So this part, which is right above the spinal cord, it's, any human, no matter how far back you go, has had that part, because the newer parts are more along the top covering of the brain. We'll talk about that later, the cerebral cortex. Let me get my pointer going again. So at one time the brain was smaller, but even if it was smaller, it would still have included all of this region here. What's new, the newer part is it's kind of expanded outwards. It's gotten, so these areas up top that I'm showing you, they're more advanced parts, and they're going to be responsible for more advanced functions, as man learned to speak, and as man learned to use numbers and through algebra, things like that. You're going to be using this this cerebral cortex here, which we'll talk about later, to do those higher types of processing. So what we expect in this hindbrain is very basic functions, and this is what we find because they've always been needed. So let's go through them here. The medulla regulates breathing, heartbeat, and other vital functions, such as blood pressure, nausea, vomiting. So they're all associated with the medulla. Well, that's pretty important to have your breathing and your heartbeat regulated. So it also makes sense that it's really low down. So like it's because it's lower down, the messages will get back and forth between your heart and your brain quicker, and between your lungs and your brain quicker, to keep your heart beating and to keep your lungs breathing and things like that. So really basic functions. Next we have the pons, colored dark blue here. Pons translates to bridge, because it connects the cortex, this higher area, to the cerebellum, which is shown over here, which we'll talk about next. It doesn't really, it's hard to see it here, but apparently it connects the cerebellum to the cortex. And that's why it's known, that's why they got the word pons or bridge. You can see some other things that it regulates here. I'm not going through everything that's already written on the screen here. The cerebellum, going back here, that translates to little brain, because it kind of looks like a miniature brain. It plays a predominant role in our sense of balance, and it enables us to coordinate movements and to learn motor skills. Especially things like well-rehearsed movements or very fine movements, like if you're threading a needle, your cerebellum is really important for that. And well-rehearsed movements, like let's say you have a dance routine you've been learning, the cerebellum is going to play a role in that. Or if you play a musical instrument, like that's a well-rehearsed set of movements. Athletics as well, with swinging a bat at a ball. You're coordinating a lot of different information at one time, and in different movements at one time in order to hit the ball. So it doesn't initiate, it's not what initiates most of our voluntary movement. I'll talk about that later. That's higher up, but it helps to coordinate movements. It is susceptible to alcohol, which is why they have you do things like stand on one leg, for a roadside test, or to walk a straight line, or to, touch your nose with your eyes closed, things like that, because, you know, the cerebellum is really important for balance. And this is why if you drink too much, you start to stumble, and it's hard sometimes to keep your balance. Okay, let's move on. That is the hindbrain. Okay, there we go. Okay, oh yeah, moving on to the midbrain, and I guess this is the same picture, but uh, the midbrain contributes to movement as well. And it contributes really to tracking of visual stimuli. It's really important for that. For instance, if you let's say you're keeping your eyes focused on something as your head moves. So like stare at some spot on a wall or something, and then move your head left and right. Like you can keep your eyes on, staring at the spot. Like as you move your head to the left, your eyes don't automatically shift. If you want to keep looking at something, you can move your head all around and still keep your eyes focused. This part of the brain is really important for that. Um, what else? It it also contributes to reflexes that are triggered by sound, such as jumping when we're startled by a noise. So all of a sudden a loud noise happens, or and then or somebody sneaks up and scares you and yells at you from behind you, and you kind of jump. I mean, that's coming from that part of the brain. That's coming from the midbrain. Okay, the substantia nigra is important for as it says here, the initiation of voluntary motor activity. And this region is critical for the production of dopamine, one of the neurotransmitters in the brain. If you remember, it's a neurotransmitter. It's responsible for motivating behavior, and it helps to control normal motor function, movement functions. And this is why I mentioned Parkinson's disease in the last video. It's caused by the death of substantia nigra cells and the resulting loss of dopamine produced by those cells. So you need that area to produce new dopamine, and if you get Parkinson's, then you lose cells out of that region, and this is why you lose dopamine, and this is why you lose a lot of voluntary movement control. Okay, let's go on. That is the midbrain, and the midbrain. So like these are really much smaller parts than the main brain. So we looked at the hindbrain, which was the cerebellum in these lower parts. And then the midbrain is right here where the substantia nigra is. But it's a very, very small part of the brain. And now we get to, sorry, this isn't working. Okay, there we go. Now we get to the forebrain. Just to backtrack, the forebrain's all of this brown colored area. Okay, this is the forebrain. So it's most of the brain. It's the biggest and most developed area of the human brain. It gives us our advanced intellectual abilities. It it has two major areas. Um, the majority of the forebrain is composed of the cerebral cortex. I'll talk about that more later. And the other area is the limbic system, which is considered the emotion center of the brain. It also has a role in smell, motivation, and memory. It has four subcortical structures. The word subcortical simply means that these structures are under the cortex. And you can see, like, just going to this diagram on the next slide, this is the limbic system in here. It's right above the midbrain that we just looked at, but it is part of the forebrain. The cerebral cortex is this whole light blue area. So you can see the limbic system is a small area kind of buried in the middle of the brain, and and these structures are subcortical because they're below the cortex, below the cerebral cortex. Okay. Let me go through parts of the limbic system. We have the thalamus, It relays information from the sense organs to your primary sensory cortex. Um, it's been nicknamed the relay station because you know all of your sensory information passes through there before it gets processed in other areas. So it does some initial processing, but then it moves the information on. It's not like the final destination. So this includes, your touch sensations, your visual sensations, your auditory sensations, as well as your taste sensations. They all pass through the thalamus, all those different sensations. But then they all go on to specialize. Those messages go to specialized areas for final processing. So it's a relay station, and it's a temporary stop. The hypothalamus regulates and controls your internal bodily functions. It controls, for instance, the pituitary gland, um, and it's been nicknamed the master regulator because it regulates a lot of uh, um, bodily functions and basic, um, I don't know, survival functions. I don't know what to call them, but it regulates hunger, thirst, sexual motivation, and certain other emotional behaviors as well. It also helps control your body temperature. So it's got a number of kind of basic functions of telling you when to eat, when to stop eating, when you're thirsty, you need to drink, and you know when you want to have sex and things like that. So the master regulator, the hippocampus plays a role in forming new memories. Um, I will tell you though that it's the memories don't stay there. Okay, like if I was to damage your hippocampus, or not me, but let's say you had a brain injury that damaged your hippocampus, you may have trouble forming any new memories, but you would still have all your old memories because even though you need the hippocampus to form memories, the memories end up being stored in other parts of the brain. But without a hippocampus, you can't form a new memory. It is an area that's affected by Alzheimer's disease, and we all know that memory problems are a big part of Alzheimer's disease. Okay, let's go on. The amygdala is the last one here. It plays a key roles, excuse me, in fear, excitement, and arousal. Um, Going on, and let me go on to the picture. Just kind of quick review here, and maybe I'll add a couple things if I miss them. But so I'm going to go start with the thalamus, and then go clockwise. Uh, Remember, it's the relay station. It for all of our senses except for smell. Smell does not go through the thalamus, but all the other four senses do. The hippocampus, um, remember, it's where it's needed to form new memories. Also, one thing I didn't mention is spatial navigation. It's involved in. The amygdala is involved in memory processing as well. Um, oh, sorry, memory process. Sorry, I was looking at my notes here. I wanted to add that's involved in memory processing during emotional arousal. Uh, um, but remember, it's also kind of known as a place where we experience certain intense emotions. I mentioned fear, excitement, arousal, but it's really important during these emotional events. It's really used to help create memories during those times. Then going around, we have the hypothalamus shown at the bottom there, and or listed at the bottom. Remember, it's nicknamed the master regulator because it regulates basic functions like hunger and thirst and body temperature and arousal, sexual arousal. Also motivation. I don't think I mentioned that one earlier. And then going up to the top, we have the cerebral cortex, that big light blue area, and it is the newest part of the brain. I mentioned that when I talked about the hindbrain, that was the oldest part of the brain. Like back when humans had much smaller brains, you always still had a hindbrain. and control basic functions. But as humans have evolved over the whole human history, our brains have gotten bigger. They've expanded outwards. So we know this newest part of the brain is going to be for more advanced kinds of functions, and such as, you need it for things like language, or to work with numbers, or to, newer human accomplishments. Um, uh, let's go on then. We'll come back to the cerebral cortex again, actually on the next slide. So let's go there now. So the outer layer of the forebrain is called the cerebral cortex, and the word cortex comes from the Latin word for bark, because it's the outer layer. So it's kind of like the outer layer of a tree is the bark. So they called it cerebral cortex because it's the outer layer of the brain. However, it doesn't feel like bark. If you ever felt a brain, it feels more like jello. Its brains are pretty squishy, and it's folded over many times. You can see, the folds within the brain here. It's like all kind of folded in on itself. If you actually like expanded this cerebral cortex, if you like flattened it out, it would be about the size of a newspaper. Okay, it is where we have our thoughts, our perceptions, and it controls all of our complex behaviors as humans. Um, the Where am I going here? Oh, okay. The cerebral cortex consists of two cerebral hemispheres, the left and the right. So two halves of the brain, and they're connected by the corpus callosum, which allows communication between the two halves. Um, I will mention that this picture might be out of order from the, if you print out the slides. I made a slight change, moved this slide earlier where it belongs. Okay, so this is the this is showing the two hemispheres of the brain, the left and the right hemispheres, or the two halves of the brain. And the only thing that connects the two sides of your brain is this corpus callosum. It's a large band of fibers that connecting the two halves, and messages like rapidly go back and forth between the two halves of your brain. Um, there's something called split brain surgery that used to be performed where they would actually cut the corpus callosum, uh, right down the middle, and basically splitting apart the left and the right hemispheres. And this was done to treat epilepsy back in the day. Um, and when somebody underwent a split brain surgery and had their hemispheres separated, so they would cut right down the middle. You can see where that line is. Just imagine like they just slice right through there. So now the left and the right hemispheres can't communicate anymore, and they end up functioning independently. Like it's like you have two brains in a sense because they don't communicate. Um, they 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 don't coordinate things as well. It's almost like you have two sets of two different brains that are may give you different sets of instructions. For instance, they did a lot of studies on split brain patients, uh, and it revealed these studies revealed important insights into how the two hemispheres are specialized for certain functions, because it's hard to study like what the left versus right side of the brain does. Um, when we know that messages go back and forth very quickly all the time. It's like you always in a normal person, both the two halves of the brain are working together all the time and sending messages back. Send messages back and forth. In the split brain patients, we could kind of study like what's the left side doing, what's the right side doing, and we could find out what each side was more responsible for. Be in kind of interesting experiments, and knowing that they can't send messages back and forth. So they would do experiments where like they would show somebody a word or a picture, and they only went to one half of their brain, and and so we could test like how each half of the brain responds differently to things. I'm not going to get too far into it now, but finding out like what each half of the brain was specialized in, this is known as lateralization. That each half, has different functions. They're not like identical. Um, for instance, each hemisphere of the brain controls the opposite side of the body. So, like, if I move my left arm, that signal comes from the right hemisphere of my brain. If I move my right leg, it's coming from the left side. So everything it crosses over, including vision. Like if I'm staring straight ahead, everything to the to the left of like, let's say I don't everything. If I'm staring at a dot of my ball. Everything to the left of that dot is going to the right side of my brain. Everything to the right of that dot's going to the left side of my brain. Like you never notice this because you just, like I said, we both sides coordinate information, but we've one of the things we found out was that we have this crossover function that everything that you feel or every movement you make on one side is controlled by the opposite hemisphere of the brain. Okay. Also, we found out that there are some specialized functions in each half of the brain, in each hemisphere. The left half is I'm just going to mention a couple things. Is usually the main half responsible for language as well as logic. And this is an easy memory aid because they all start with L. Left hemisphere, language, logic. Okay? The right hemisphere is very important for spatial relationships. I'm not going to get into what that means, but also face perception mainly comes from your right hemisphere. Okay, and you can read more about that in the book as well. Okay, there are 4 lobes of the brain. We can divide the cerebral cortex into 4 sections or lobes. They're listed here: occipital, parietal, temporal, and frontal. Let's take a look at these 4 lobes of the brain, and we'll begin with this picture here, and I'll go through the 4 lobes. So the lobes are all listed in this left diagram: frontal, parietal, occipital, temporal. In this right diagram, I'm going to tell you about certain important functions that are in each lobe. And you do need to know these. We could test you on any of these. So I'll mention a lobe and then I'll mention some of the specialized functions in it. So I'm going to start with the occipital lobe, right at the back of your brain, small area at the back of your brain. It's specialized for vision. And you can see over here, it contains what's called the primary visual cortex. That's where we process all of our visual information. So I'll just tell you, when information comes in through your eyes, you have no idea what you're seeing until um, the message reaches the primary visual cortex. This is where you make sense of what the information is coming into your eyes. So in a sense, like you don't really see with your eyes. They're instruments to let light come in, and then we have no idea what the information is until this primary visual cortex processes it. Okay, so anyways, that's all you need to know about primary visual. About the occipital lobe is responsible for vision. The parietal lobe, going kind of towards the back of your head, of your brain, I guess I should say. It contains a specialized section shown here in this dark purple called the primary somatosensory cortex. So this processes a different sense. This processes touch sensation. So it's sensitive to things like pain and temperature and touch sensations. So, like if I touch anything, or if anything, let's say a bug lands on my arm, or I don't know, the sun is making my skin hot. I mean, so any kind of touch sensation, it gets processed here, and that's right at the front part of the parietal lobe. Okay, let's go to the temporal lobe. It's pictured on the left here in green. So it's the lower part of the cerebral cortex, and it plays a role in hearing, understanding language, and storing autobiographical memories. Autobiographical memories means memories about your life, like memories in which you were there, and remembering events from your life and things that you've done. Not like we just remembering facts or things like that. That's a different part. But anything like personal memories are autobiographical memories, and this part of the brain helps to process those. So it contains, I mentioned, understanding language and hearing. So it contains the primary auditory cortex. So this is the third um, third the third out of four primary cortices that we'll be looking at. We talked about the primary visual cortex, primary somatosensory cortex. This is the primary auditory cortex. All sound information is processed in this area, part of the temporal lobe. Another part of the temporal lobe you need to know is the fusiform face area. And this plays a role in recognizing people's faces. You can see it's a small little area towards the back of the temporal lobe. And if that part was damaged, you would have trouble telling faces apart and recognizing people, because it has happened. There are people that have had that damage, and they can't, they wouldn't recognize their own mother, by looking at her face. Okay, interesting thing that you have this small area damage, and you'd still see faces, but you just can't recognize them, even if you know them. Okay, moving on to the last lobe. It's called the frontal lobe. It's this large orange area over here. It oversees and organizes most other brain functions. It's kind of like your control center. It really is. It's kind of like it's the part of your brain that controls your thinking and controls your decision making and things like that. And what else do I want to say here? Okay. And I will talk more about it later, but one of these specialized areas you can see here, the primary motor cortex. This is the last of the primary cortices, and it is responsible for voluntary movement. So, moving your legs or arms or any other kind of voluntary movements. And so you can see it's at the very back of the frontal lobe. It's right next to the primary somatosensory cortex. This is actually important, and we'll see this on an upcoming slide. Just notice for now, they're right next to each other. This one, the somatosensory cortex, is responsible for all, bodily touch sensations that you receive. This is in the motor cortex, it's for all voluntary movements that you make. And we'll find out why they're next to each other. The other part of the frontal lobe is this large pink area shown here called the prefrontal cortex. I'm not going to get into it now. You can see it lists attention, self-control, social processes. It is really kind of our most important part of our brain in a sense. It is, and once again, I don't want to get into it now. I'll talk about it later. I'm going to come back to that. So anyways, you do need to know these areas. You need to know the four lobes, and you need to know all these cortices I talked about. Let's go on here. So some of these things I've already talked about a lot of these. So remember this, just real quick review: occipital lobes. Remember this mainly for vision. The parietal lobes At the top of your head. It's got that area for the sense of touch, the somatosensory cortex. What I didn't mention is it's also important for picturing the layout of spaces in an environment. Okay, going on now, we're going to get to what's called the homunculus, and this. So I just said that it's going to be important that the somatosensory cortex and the motor cortex are next to each other. And what we're seeing here is a mapping of the areas of the motor cortex and the somatosensory cortex. Remember, the primary motor cortex is at the very back of the frontal lobe. It's for voluntary movement. The primary somatosensory cortex is at the very front of the parietal lobe. It's for physical sensations. And somebody mapped out these areas um, and created this homunculus. Homunculus means little man, little man. And basically, what he mapped out was like what each area was responsible for. So if I look at the motor cortex, like, this area over here on the left where my pointer is, this is the area of the motor cortex that controls your tongue. This is the area that controls your jaw and your teeth and gums. And then you got this large area for your face. And then, pretty large area for your hand and fingers. And then you got some smaller areas for things like your arm and shoulder and neck and trunk and and hip, and the foot's a little bit bigger too. But and if you see over here, and so this is like initiating movement of all these areas. Over here is getting feedback from all these areas, like sensations back from all these areas. And so these areas are right next to each other. So this facial area that where you direct your facial muscles to in order to speak or to smile or to do any kind of facial movement, it turns out that it's right next to the facial area that receives that receives sensation information from touch and whatnot. And the reason why it's important, like if you push these two halves together, like they're right next to each other, because all of our movements depend on a feedback system. Like when let's say I'm walking, I I'm directing my each leg, one after another to move forward as I walk. But I need to know, like, when one foot touches the ground, and as I move from heel to the sole of my foot and like to my toes, like, you have to have constant feedback to know, like, how to make your next movement in a sense. And so, because they're right next to each other, they can send messages very quickly back and forth. So, this facial part here is right next to this facial part here. So as I'm moving my mouth and my lips and my tongue right now and my jaw in order to talk, I'm also getting feedback about, like, I can tell as soon as my lips touch, in which, and I can tell where my tongue is in my mouth, and because I keep getting this feedback sensation. And so, they would be looking down this bomb diagram, like they would be right next to each other. So if this was my facial part here for movement, for causing movement, this would be my facial part here for getting feedback from my face. So boom, 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 it makes so much sense that they end up next to each other in the brain. So because you need them to work together. What's interesting, and you may have noticed, is that look how large, like for instance, the facial region is compared to something like the trunk area. Like there's this little area for the trunk here. Like your trunk is a lot bigger than your face, but your face is huge compared to that trunk. Well, obviously, you don't direct a lot of movements in your trunk. You can move it about a little bit. You don't have a lot of fine movements. It doesn't contain a lot of different types of muscles. Think about your face, all the expressions you make, the all the movements you make to speak, for instance, or even to chew food. Like when you speak, you're coordinating your tongue with your lips, with your jaw, with other facial muscles. Show emotions. You have so many different muscles in your face. This is why it's such a large area. You have a lot of intricate muscles within the face, and just look how much is devoted to the mouth. There's a whole area for the tongue, a whole area for jaw, teeth, gums, for lips, and this is taking up a large area compared to the rest of the body. And same over here for the feedback you get, the sensations. So that's interesting. The more you use a part of the body, the more area is going to be devoted to it. And by the way, this can change over time. They did a study where they looked at um, violin players that have been playing for years and years and years, and what they found is that their their left hands, like if they're right-handed, they would hold the bow in the right hand, but the other hand would do all the intricate fingering. Well, the areas in their motor cortex and somatosensory cortex for their left hand actually grew bigger than for their right hand because they had been using their left hand so much for years, doing little finger movements, touching the strings and whatnot. And this be similar probably for a guitarist, but they studied violinists in this one study, and it changed over time. So if you keep using certain muscles, a lot, and they become important to you, and that area is going to grow. Similarly, if you were to be paralyzed in part of your body, that area would shrink because you're not using those muscles, you're not getting feedback. Okay. So, anyways, these are the mappings of the motor cortex and the somatosensory cortex. They were created by a man named Wilder Penfield. His name is Wilder Penfield. And he created the homunculus mappings as he examined patients who were to undergo surgery for epilepsy. And so we see one of his patients here, and we see the exposed brain of the patient, and he would test them while they were awake. So they would be awake with their brain exposed like this, and he would electrically stimulate different regions of the brain, and he would ask the patients to report what they were experiencing. So he was able to map out those areas of the brain. So, if let's say he hit the leg region of the somatosensory cortex, the patient would say, "Oh, I'm feeling a sensation on my leg," or if he hit the motor cortex, he might actually cause them to all of a sudden jerk their hand upwards or something, or to make some other kind of involuntary movement if he stimulated the right area. So he was able to map out these regions here with these patients and create this homunculus diagram. Um, um, you know, some people have questioned the ethicalness of this. I mean, like he really did have to. He did have to stimulate the brain, so he was trying to find which areas caused their epileptic seizures. And but what I've heard is that he did a lot more exploring than he needed to with these patients in order to map out the brain. Okay, let's go on. Okay, just these are coming up now. I already talked about them, but a couple of reminders. The temporal lobes, remember they're at the side of the brain, at the lower part of the sides. Um, they're important for processing auditory information and also for perceiving objects and faces. I mentioned that area for perceiving faces, but it's all this lobe of the brain also helps to perceive objects. Frontal lobes, just a reminder, we have that motor cortex, so as part of the frontal lobes to initiate all your movements, voluntary movements. And also the prefrontal cortex is important for complex processes like rational thought, attention, and social processes. Let's look at the prefrontal cortex a little bit more on the next slide. So, as it says here, it occupies 30% of the brain. Remember, it was that large area. It's right behind your forehead. And they say that the difference between the human brain and brains of other animals lies in the complexity and organization of prefrontal neural circuits. We have our prefrontal cortices are much more advanced and interconnected. And this is what makes us different from animals. Um, People say, the researchers say that the prefrontal cortex is correlated with our highest capacities as human beings. So things like morality, empathy, um, a connection to others, your sense of self. It's also responsible for rational thought, decision making, planning, impulse control, directing your attention and maintaining attention on things. Um, so I mentioned earlier is your frontal cortex is like your control center. I mean, it's making decisions, it's planning, it's controlling your impulses. It's basically your consciousness. You know, it is basically your consciousness. It's what the part of your brain that you're using right now to think, what do I want to do next, or like, or to try to remember information, or if you're taking notes right now, like you're using your prefrontal cortex to do all these things. Um, in a sense, it's really who you are. In many ways, it's who you are as a person. You Because it controls things like morality and empathy and connection to others and sense of self. Like it is by far the most important part of the brain. Um, you could have other parts damaged if your, you know, visual cortex was damaged. You might never see again, but you'd still essentially be the same person, just to you'd be blind. I mean, your auditory cortex was damaged. You might not hear again, but you would still, you know, you would still have your same sense of self and morality and things like that. But this area is like it's really what defines us as humans. I can, it's the part that you it would be the part you would least want damaged. So this brings me to my next point. Well, they used to damage this part of the brain on purpose. When they used to perform lobotomies, they would they would drill a hole either in the side of your skull, like kind of where your temples are, or sometimes right above your prefrontal cortex. They might drill a little hole. It was they would drill a hole through your skull, and then they would insert an instrument and damage part of your prefrontal cortex. This is what a lobotomy was. Just kind of purposely damaging, and it wasn't a well controlled um, procedure. Like brain operations today. Um, they did this in order to reduce tension or agitation in patients. Um, Often it was performed in mental institutions. If patients became too agitated, for instance, they might do a lobotomy and it would make them calmer. Um, anyways, the problem was like it often did work as far as making people calmer and less agitated, but it could also severely negatively affect the patient's personality, their ability to function independently. I mean, some people couldn't, couldn't live by themselves after this. Um, they often showed substantial reductions in initiative and also in inhibitions. Remember, impulse control is important, so like for in that area of the brain. So some of them would start like people that may never war before, all of a sudden like they're swearing like all the time, or they're doing drinking a lot, or whatever. Like they would often change who the person was. They would change their kind of basic personality, um, and a lot of them died as well. I mean, this I read one of the main person that performed these, like apparently he had about 15% fatality rate, which is pretty high. Um, and it was a controversial procedure, but it actually went on for quite a while. But it was, eventually phased out after we discovered psychotropic medications. Once the era of drugs came, mental health drugs were invented, and around the 1950s, in particular, 1960s, it started to be phased out, because that's when we really started to come up with drugs to help people with problems. Okay. Oh, I'll just mention, if anyone ever saw One Flew Over the Cuckoo's Nest or read the book, I mean, it was in that old movie. Jack Nicholson was the star, and he underwent a lobotomy at the end, and like he basically became like a vegetable. Like, he was a extremely um, charismatic kind of. He was in a mental institution, but very charismatic and loud and talkative. And then he underwent the procedure and just basically sat there. And that's kind of what lobotomy could do to you. Okay, one final slide here. This is kind of like it's an early unplanned lobotomy. Okay, this was back in 1848. A guy by the name of Phineas Gage. He was like 25 years old and working on the railroad, and a railroad spike. You can see him holding it there on the left. So it's a really long spike. There was a blast that sent it up through his cheek and through his skull. You can see the picture over here on the right where it went, where the spike went. So it went right up through the prefrontal cortex area of the brain. And he survived. I mean, miraculously enough, he survived, and they kind of studied him as a case study afterwards. And his personality radically changed. Apparently, he was a good family man, a good worker. And then he started drinking a lot. He ended up getting divorced soon after. His inhibitions disappeared. He would go after women all the time. Like he just became a very different person. Um, and so this was kind of like an early case study of what happens when a spike goes through your prefrontal cortex. And that will conclude learning objectives 3 and 4. Oh, need to stop the recording.